Welcome back, everybody. Short break there, but we launch right into the next presentation, and that is Detecting and Mapping Unmarked Cemeteries with Archaeological Geophysics by Dr. Jonathan Fowler. Dr. Fowler is an archaeologist based at St. Mary's University in Halifax, Nova Scotia. He's interested in the application of modern scientific instruments and methods to archaeological questions, and since the 1990s has been mapping the lost settlements of pre-deportation Acadie. His most recent book, co-written with Earl Lockerbie, is Diaries of the Acadian Deportations, Volume 2, John Winslow at Grand-Pré, which explores one of the key primary sources relating to the 1755 deportation of the Acadians. So, welcome, Dr. Fowler.
Good to be with you. Thanks for the intro. Shall I share my screen?
Please do.
All right. Let's see. All right. Speaking of Grand-Pré, we should see it.
Looks great.
All right. Well, thanks again. And I'll launch right into it. I'm a little concerned about time, of course, and want to make sure we have ample time to have a bit of a conversation about this as much as anything. And I recognize from the outset, this is a little bit of an unorthodox presentation, probably for a conference like this. And the whole thing is sort of based on the notion that genealogical research, historical research broadly, I think takes on an added significance when we add the dimension of place. When we're not just doing the research, more or less in our heads or just using text, but where we can actually connect with the geographies of ancestral people. And there's perhaps in the spectrum of human interactions with the land, there's perhaps no more intimate connection than the presence of human burials in the landscape. So places where people were buried either formally, as in the case of this title slide. This, of course, is the old Acadian parish cemetery at Grand-Pré National Historic Site. So either these formal places of interment and commemoration, or even we have a range of sites that are rather informal, sometimes even in the world of law enforcement and forensics, clandestine burials. And nevertheless, these are significant places that will sometimes connect to your research. And so for those of you who might have asked the question, how would I find the grave of somebody or of this community? I just thought I'd gather my conversation or gather my words around that question. So detecting and mapping unmarked cemeteries with archaeological geophysics. And in this presentation, I'll look at 3 case studies. But before we get to the case studies, we'll take a peek at some general considerations, including, I have to say, a little bit of theory. Now, I will say this, though, before launching in, I'll probably pause at least once or twice and ask for questions. So rather than wait to the end, which we will also have question time at the end and discussion time, I'll make a little bit of room throughout. So hopefully we can spend a little bit of time having that chat along the way. So this is an excavation trench that my students and I dug at, again, Grand-Pré National Historic Site, about a decade ago. In fact, it was 2013. And you can see for reference, the memorial church in the distance, the stone monument, Herban's Cross, kind of in the middle distance. This monument was built round about 1908, 1909 by John Frederick Herban, who was a kind of an interesting guy, a bit of a polymath, sort of poet, writer, historian, politician, businessman, in the way that all of those categories tended to get blended in earlier times more easily, I think. Well, interesting guy. He played a role, was instrumental indeed, in reserving this parcel of land as a memorial site. He purchased it from a farmer, and one of the main things that really incited him to do this was the knowledge that antiquarian diggers and treasure hunters were digging on the site in the cemetery, in the old pre-deportation cemetery, and excavating excavations and perhaps human remains. And he wanted that to stop. He wanted to protect the site. And so he purchased it with some colleagues and set about establishing a memorial site. He created that stone cross, which is where he thought the original pre-deportation Acadian cemetery was located. We don't really know on what basis he made that diagnosis, although, as I said, other diggers were working in the area and excavating, so perhaps he knew the general location. Right. Well, this site, incidentally, this is not going to be a presentation about the pre-deportation period or anything like that, but just to put it on the map for those of you who may not be very familiar with the history or the geography, Grand-Pré National Historic Site of Canada is located in the community of Grand-Pré, just east of Wolfville, Nova Scotia, and it is at the center of what is now, since 2012, the landscape of Grand-Pré World Heritage Site, a UNESCO site. And this was a village, basically, which was destroyed in 1755 by New England soldiers, and the French and Catholic population was deported, and the community burned. So this is said to have been the site of their parish church and cemetery, and it's been the site of some of our excavations in recent years. Now, what you're seeing in this photograph is one way that we can ascertain the presence or absence of unmarked burials. So wherever we are, we will have this option. But as you can see already, just by judging from how many people are present, it's a rather labor-intensive process. This work took us several weeks. And what we did here, I should emphasize, is that we didn't dig up the graves or make any direct contact with human remains or coffins or anything like that. What we did was we removed with hand tools, in fact, trowels, the upper 20 or 30 centimeters of the soil only. And this is the area that had been previously plowed and mixed. So we removed that to expose the subsoil. And when you can see the subsoil, you can, if you're lucky, if the conditions permit, and if you're careful, you can see what are called grave shafts. So these are the holes dug into the ground through the natural soil column and then backfilled after the burial has taken place. And the distinction between the backfill and the surrounding soil allows us to discern the presence of the burial, the grave shaft. And so here I outline them kind of roughly at this scale, but we'll take a look at the far end of the trench toward Herman's Cross. And this gives you a slightly better perspective of what these things can look like. And again, we've only removed the upper 20 or 30 centimeters. That's a 1 meter scale bar there at the end, just to give you a sense of it. And I've scored with my trowel the edges of the graves in this case. So these graves are here and here. Now they will persist. They'll go down further, perhaps a meter. The graves in this period tend to be fairly shallow. So that's another consideration that we need to bear in mind. We're not often looking for a 6-foot deep grave shaft. That's more of a modern thing. These tended to be much more shallow. So we're putting on the brakes basically below the plow soil because we don't want to get into the graves. We just want to map them and detect them. So that's the kind of basic orientation to the problem and one of the ways in which we can obtain evidence. If you have a question, in that field over there, is there an unmarked cemetery, a forgotten cemetery? Let's assume there are no stones. Can I find out? How can I do this? Well, this is one way. You would have to get landowner permission. You would then have to get an archaeological research permit, depending on what jurisdiction you're in. Here in Nova Scotia, that is administered by, on private land and provincial crown land, that's administered by something called the Nova Scotia Department of Communities, Culture, Tourism, and Heritage. It keeps getting reorganized, but that's the entity presently. Or if you're on federal land, national parks, national historic sites like Grand-Pré, it's a Parks Canada permitting process. But you need a permit to undertake this kind of work. so that it's done by people who are qualified and experienced, and it results in a reporting sequence. So any of this work that's done will result in reports that get filed with the government. So there we are. But let's just say you're not really keen to undertake this kind of digging. Very labor intensive, as I said, and kind of labor intensive on the permitting side as well. What are your other options? And your other options include this world called geophysics. So geophysics basically involves using instruments that were really not designed for archaeology. They were designed for other industries. But we're using these instruments which measure different electromagnetic properties of the soil to determine the presence, absence, the nature of archaeological sites and features. So it's a way of detecting material in the ground without direct observation. In other words, it's a non-destructive technique. It's a way of scanning, not altering anything, but obtaining information. And I like to introduce that subject with this image of this owl hiding, because of course archaeological features are in a sense hiding from us in the ground. And though we may apply these tools and techniques, and we may have experience and training, this is not ever an easy process. And in fact, unmarked burials are among the hardest targets in the whole realm of archaeological geophysics. So as we launch into our discussion here, it's also a bit of a caveat. Don't let anybody tell you that it's a very straightforward proposition to measure and detect and map unmarked burials. In fact, it's very difficult to do. And sometimes factors prevent us from being able to do it effectively. And sometimes it's just in a setting or in conditions where it's just not going to be very easy to do. We discuss research design. So how do we get a sense of, how to approach these things? These are the 4 considerations that I always keep in mind when I'm looking at sites like this. And the first at the upper left is the nature of the target itself. This will be determinative to some extent of the rest of the research design. What is the nature of the thing we're trying to detect? And going back to our owl friend for a second, graves are very much like this owl in the sense that there's not a sharp contrast or distinction between the appearance of this owl and the appearance of the tree that the owl is hiding in. Just like that is the case visually, geophysically, when we look for unmarked burials, there's not a strong contrast between that grave shaft and the soil on either side of it. And that's what makes it so tricky. So the nature of the target is important. It'll help determine what kind of instrument we use, which, as you can see, that's another one of our considerations. In this presentation, I'm really going to focus on ground penetrating radar, but I'll bring in a little electrical magnetic instrument to show how complementarity helps us as well. So the nature of the target, that will help determine the nature of the instrument. Radar is one of the better instruments for looking for unmarked burials. The nature of the ground, so the field, I'm referring to it here, and that includes everything from vegetation at the surface to the nature of the underlying geology. The more you know about the setting, the better. And many has been the time in my work where I've been asked to work and look for burials or look for other features in, say, a forest or an area that's really heavily overgrown. And one of my first statements to the people I'm working with is we have to clear that. That's got to go, because you can't get the equipment into an environment like that. So really the ideal environment is something like a golf course, very closely cropped vegetation and soil, and away you go. Forest, alders, any of this kind of overgrown stuff that you get on former settlements it's a problem. And finally, this thing I'm calling survey strategy, how we deploy the instruments and I'll get back to that in just a moment. You can be cursory, you can be extraordinarily careful, and there's a spectrum in between. And in general, the more time you spend in the field, the more data you collect, and the more carefully you collect it, the better likelihood of success. So this is not time for quick passes and, drive-by geophysics. You want to spend some time and collect quality data. Right. So getting on to the instruments and techniques, there are different instruments that can be used in archaeological geophysics. Some of them you may have heard of before, starting on the far right, of course. Resistivity is looking at how easily or with what difficulty, more properly, an electric current passes through the soil. This can sometimes detect burials. Magnetometry, just very slight variations in the Earth's magnetic field, which can be measured with very perceptive instruments. These can also be instructive. Unfortunately, passive magnetic methods can sometimes be blown out just by changes in geology. There are certain places where you've got, say, igneous rock near the surface, and it prevents you from using this method. Next one over, this thing called electromagnetic induction. I will speak a little bit more on that one because that instrument right there is our own EM38B, covered in mud. And it's a very useful piece of equipment for getting complementary data. But the main one that we're looking at here is this one on the left, ground penetrating radar, or GPR for short. And it looks like it's in a tropical environment, but it's not. It's in Halifax's public gardens in the tropical section. So there you are, ground penetrating radar, mounted in a cart in this case. Now, radar is a very old technology. In fact, it's been theorized since, well, the 19th century at least, but in the early 20th century, there were experiments using radar waves, radio waves, basically, to measure, say, glacial ice thickness. And then, of course, by the 1930s, militaries began adopting it. And famously, this chain home battery, which we see pictured in this pretty cool way here, was part of the United Kingdom's defense against the Luftwaffe in the Second World War period. So radar has been used for a very long time, but only in relatively recent decades has it been used for archaeology. And it's been, among all the different methods, it's been one of the last to be picked up by archaeologists and used with any level of frequency, partly because it is kind of a challenging technology, and also that it produces just immense gobs of data. And it's really only since advances in microprocessing have allowed computers to catch up that we've been able to really make the most of this data. So it is a GPR. It's ground penetrating radar, and ground in this case is basically whatever's underneath the instrument. We can see the instrument here again in cart. The radar part is right in the middle. It's this little yellow box underneath, and it's more or less in direct contact with the ground, and it really kind of has to be. It's on a blue, in this case, skid plate, little plastic plate, and it slides along the ground, and this cart just kind of keeps it central. Ground is loosely defined in this case. It can be really anything. The radar wave will travel through almost everything, but there's a caveat. Soil, rock, concrete, wood, plastic, doesn't matter. Metals, it will reflect. And for that reason, if you have I've never been to a site like this, but if you have a metal surface on your site, like let's say the buried hood of a car or something, well, you're going to get a strong reflection off that, but you're not going to see below it. So beware of large amounts of metal. Like the radar gun that the RCMP might be using out on our highways, this device emits a radio wave, and it shoots, in this case, down into the ground rather than forward, and it collects responses that are reflecting off other features. And the reason why this can work, particularly in, say, guarding against the Luftwaffe or or the RCMP are using it to catch us on the highway, is because these things move very quickly. These radar waves move at just shy of the speed of light. So you can't outrun them. And the two-way travel time of that pulse of energy has reached your car and come back to that radar gun in nanoseconds. Okay, so it's extremely fast. So stacked pulses of wave energy are sent into the ground, and effectively we get reflections back, and the size, the amplitude of those reflections allows us to make maps. And I'll show you some examples of it. It's really best to think of it in this kind of metaphorical sense. I find it's just waves. It's really just waves, it ripples. Just like when we drop something in a pool of water, you see the way the waves ripple off. And in fact, this image shows it well, don't they? They attenuate, meaning they become weaker as they travel away from the point of impact. The waves gradually diminish in strength until they totally disappear. They're absorbed or attenuated by the medium. And it's the same way in the ground. So the radar wave energy is coming in. It starts very strong. There's a sharp return from the surface of the ground, for example. And then as that wave penetrates into the ground, it gets weaker and weaker and weaker. And its ability to cast reflections back that we can measure will diminish over time. Now, there are two ways of looking at this data, just to demystify this technology a little bit. The first is what's sometimes called 2D data or profile data. It's the radargram. So this is the radar data coming back to us almost as if we're slicing a cake in half and looking at the cross section. So what we have across the top, this axis across the top, is labeled in feet. 1, 2, 3, 4, etc., up to 20, 0 to 20 feet. And then depth in feet on the y-axis. And what's happening here is we get a series of kind of ripple-looking anomalies in the data. These are called hyperbolas. And the apex of each of these hyperbolas is, in fact, where we've got some kind of a point anomaly, a feature that the radar wave is bouncing off of. And the reason these things take the form of hyperbolas or upside down letter U's is because the wave energy actually emitted from the radar antenna is coming down in a cone shape. It's like an inverted ice cream cone. So it's not a direct line. So what happens is, as the instrument is being walked across this line, some of that wave energy is coming out here and hitting and reflecting back and giving us, some energy here. Some of it is coming out from the top, and some of it is bouncing off from the other side. So that's one way of seeing the data. And you have to admit, when you look at that, you think, oh, what is that? I mean, it's a very strange thing to look at. So part of the training in this kind of work is learning, by running the instrument over a variety of different targets and seeing what kind of reflection patterns those create. And as we'll see in a minute, unmarked burials create a series of very distinctive reflective patterns. And I'll show you the one that I most commonly see, at least in Nova Scotia. Okay, the other way of looking at radar data is in a 3D data format, sometimes called a slice map or a plan. So this is looking at the data from the top, just as you were looking at a map, say, of a landscape. So this is a survey grid, in fact, 2 survey grids that I did with my students a few years ago. It's 50 meters wide by 100 meters on the y-axis. So it's a pretty big area. And what we've done is we've taken slices through the data at different levels, and they're labeled. So 25 centimeters down, these are the high amplitude reflections in red. The background noise is just kind of this blue stuff. This is what's called the jet color ramp. So there's a color scale here. So the stronger reflections, the more kind of evident ripples of the wave, you might say, are in red, and then it scales down to this teal color and then background. And so as we slice down through the data at different layers, we can see the nature of the things causing reflections. And most of what you're seeing here is just natural geological deposition. So there's a kind of a wavy, this is sort of a sandy area. It's kind of waterborne sediment. You're seeing mostly that. But nevertheless, this is just to show you that we have this way of looking at maps at different levels, and they're completely arbitrary. We can look at these maps at different levels if we want, but look what happens around 2 meters down. Just like the ripples in the pool, the waves have become attenuated. So at a depth of about 200 centimeters, there's just so little wave energy reaching that point that it's just not reflecting back. This is giving us our effective depth of penetration. We're not going to see anything if it's buried under 2 meters in this case. Now, these slice maps can be animated, which I think is a really cool feature. I'm going to show you one now. Instead of the jet color ramp, I'm using a gray scale. So the more reflective features are, I believe they're in white in this case. And what you're looking at is a map measuring about 30 meters in the x-axis by about 40 meters in the y-axis. And this is a pre-deportation Acadian house at Grand-Pré National Historic Site, and it does not look very much like a house. You're going to see positive and negative features caused by drainage, tile, ditches, and things like that. And we're going to see a sort of area in the center that is the house. So here we are slicing down through the data. Doesn't look like much, but that's the cellar of the house right there at the center. Very reflective. That, by the way, that line coming out is a drainage feature coming out of the house. So they evidently had water problems. So there's like a little French drain coming out. These other linear features are modern 1970s field drains, which you don't really see very well. So this is kind of an example of how these features, fairly large structural features, can appear in a slice map. Okay, closing out radar theory before we get to our case studies. There are different types of radars, and they're designed for different things. And this is part of the stable of radars designed by Sensors and Software, which is a company based in Mississauga, Ontario, that I deal with quite a lot. Really neat people. And we have 2 radars from their stable, and they are the 500 megahertz units right here. This may look a little bit familiar because we were just looking at that. So we have lower frequency units ranging into higher frequency units. And the counterintuitive point or observation is that the higher the number, actually the shallower the depth of penetration. So the instrument over at the far right is used for very superficial types of analysis. So examining, in fact, in civil engineering and things like that, checking bridge decks and looking at rebar integrity inside concrete, things like that, where you're only going to get in a little bit. Whereas these 100 megahertz and lower, they can see far deeper into the earth, but consequently, they need larger targets because of the wave, the size of the wave. So very large targets, very deep, you would use something like this on the left-hand side. Very tiny targets near the surface, you would use one of these. Somewhere in the middle, and I like the 500 megahertz, is great for cemetery work. And in normal soil conditions, we might get a depth of penetration of about 2 meters. But that's going to vary depending on soil type. Okay, I think this is the final slide before we get to our case studies. And this has to do with this notion of survey methodology, how much time you spend in the field. There are different levels of intensity of investigation. We talk about prospection surveys, where you might have very large spaces between your survey lines, maybe 2 meters or more. We talk about delineation surveys, perhaps a meter. And then mapping surveys are the most labor intensive, but give the best quality data, 50 centimeter interline spacing, or even less. So if you're looking for cemeteries, because cemeteries are so difficult to see, we tend to work with even 25 centimeter interline spacing for cemetery work. So as you can see, more data as you go down equals more time in the field, more time processing, but better quality overall. It's very much a garbage in, garbage out kind of situation. So if anyone wants to swing by that field and look for a cemetery and take one run with the radar across it, you might as well have stayed home, because that's not how you're going to get the data that you need. Right. Here we're getting into our first case study. I'm wondering if I should pause for a minute if there are any quick questions about radar before we get into our case studies.
I actually had a quick question.
Go ahead.
Um, so, I'm familiar with some of the innovations that have happened in the last 10 years for fishing, for example, right?
Yeah.
And it's basically become like a video game for a lot of fishermen with the really high-tech sonar gear and stuff like that. Do you think that the price point on these types of equipment will ever drop to the point where it'll become commercially available for people like metal detectors or enthusiasts like that?
It's an interesting question. And I've heard, well, certainly I've observed the trend that you refer to. And especially with our mobile phones now, these things, what they can't do and what they will be able to do in another decade or more. I think of Spock and his tricorder back in the 60s, and I think we've got maybe Mr. Spock even beat at this point with the Android phone. So, point well taken. There's an analog to that with GPS. We're getting, GPS used to be military, very expensive technology. Now it's sort of run of the mill. I'm not sure that radars per se will take that road anytime soon, just because they're so complex and the engineering is so meticulous to do. But I think there are applications coming that will even allow our mobile phones to do types of very basic magnetic sensing and LiDAR, in fact, which is another remote sensing technique that uses lasers to create three-dimensional models of sites and landscapes. The newer iPhones, I'm told, have LiDAR ability, so you can create 3D models in not just using your phone. So, a bit of a shocker. Okay, we'll carry on and we'll see what comes of this. Three relatively quick case studies just to give you a sense of, illustrating how these technologies work in practice. Grand-Pré National Historic Site. Surveyed this site. There were, as you can see, over 40 different survey grids over the course of 2 years, 2.5 years, really. And in this case, we were interested in mapping buried features, including buildings, but I was particularly interested in the unmarked cemetery. So this is Herbin's Cross. I don't know if you can see my little cursor, but I'm pointing up here. What we're seeing is the pattern of rose hedges and things, but the central path is here and Herbin's Cross is here. And we've also got a depth slice map here. So I'll animate this and you can get a sense of the results of our surveys. And you see lots of drainage features, lots of buried pipes and cables. We're seeing all sorts of halos around trees. These little holes are tree stumps. These are the centers of trees, and you're getting airwaves around the trees and root systems. But right here, you'll see all sorts of little, at this scale, it's very difficult to see, but you're seeing all sorts of little features. And these are the graves. The individual burials are evident here. And at this scale, as I say, a little bit challenging to see, but we'll look at them in cross-section. This is the typical expression of graves in Grand-Pré and many other cemeteries that I've seen around Nova Scotia. You see all sorts of material in the near surface. In the radargram, nominal depth is only about 1 meter down here, so about 3 feet. And what we're seeing is a very subtle planar reflection. And they are in length, something on the order of 1 meter or 2 meters. So again, kind of body sized. And we conduct the surveys in 2 dimensions. So all the X lines and all the Y lines. And therefore we can see the morphology of these reflectors very well. And they are human body sized. So this is what we look for. We go basically line by line. There are different ways of visualizing the data. This is a kind of ISO map. So using a piece of software called Voxler, these yellow, we might call them polygons. They basically look like blobs. These are actually the three-dimensional view of the burials themselves, just to the west of Herbin's Cross. We'll zoom in here a second. You'll get a better sense of what some of these things look like. There they are. So we conducted a series of surveys in that whole area, and we're able to individually map the graves. So we've got now the ability to block out the zone of the cemetery. Looks like Herbin, over 100 years ago, he was in the right area, not at the center of the cemetery, but his cross is in the right area. And here we are again with polygons representing the individual burials, 289 burials in this case. Now, I suspect there are going to be more. The patterning of the burials is quite interesting. One of the things that intrigued me about mapping this site and mapping other early cemeteries is trying to understand the patterning, just the spatial patterning of the burials. Are there, is there a section for children only, or, are there zones where there are clusters, family groups? Can you perhaps discern that? And it does seem to be the case that children are interspersed, and there do seem to be certain clusters, like the ones I just showed you were right here. Some of these graves actually are very difficult to visualize because they intercut a little bit, or they're superimposed one on top of the other. But nevertheless, this is kind of the preliminary map. I'm going to go to the Battle of Grand-Pré as our second case study. But actually, it occurs to me, I thought I had some additional graphs. I'll come back to this Grand-Pré cemetery in a minute. Battle of Grand-Pré, similar neighborhood, similar geology, similar time period. But this was a battle fought in the center of Nova Scotia in Grand-Pré in the winter of 1747. So here we see a early 20th century depiction of the scene by noted artist C.W. Jeffreys, and it's depicting the moment at which the French attackers surprise the New England soldiers, and they come storming out. The New Englanders come storming out of a house, and they're getting picked off by the French and indigenous attackers. Really quite a fascinating battle. Now, as a result of the battle, something like, we don't really know the number of killed and wounded on the French side, but it seems to have been very few. But the number of New Englanders, or Massachusetts guys, killed is in the 70s. So 70 odd people killed, including the commander, Arthur Noble, and his brother Francis, who were apparently buried in two graves off to one side. And the bulk of the New England soldiers killed and officers were buried in a single mass grave. Now, there's a lot of information about the locations of these graves, which we can discern from historical records, but on the surface today, they're just gone. They're no longer marked. The sites are no longer remembered. So part of the research that we've been doing in recent years has been trying to determine the location of this mass grave. And 2012, we employed dogs. There was a group that came up from the United States to teach a course at St. Mary's in the forensics program, a course on cadaver dogs. So these are dogs who are trained to detect the scent of human remains, and they alert. They give a sort of signal to their trainer when they smell this. It's along the same lines of when you have dogs who are trained to detect bombs or drugs in the airport, things like that. Dogs can be trained to detect human remains as well. And this technique may sound a little bit far-fetched or almost science fiction, but I assure you it's not. The dog you're seeing here at the bottom was able to detect, they told me in Europe, I think in the Czech Republic at the time, a skeleton that was 6 feet down and something like 600 years buried. So it is possible. So these dogs, I didn't tell them precisely where I thought the burial was, the mass grave, but I said, I think it's in this area. And we let them and their trainers go out and do the work. And sure enough, the dog alerted and said, I think it's here. I took the GPS coordinate and only later came back with the radar. And when we did, lo and behold, in the area the dog had identified, there was indeed a very kind of complex and lengthy planar reflector at some depth. Here it is in kind of length and width dimensions, and the little graphic at the bottom right gives you a sense approximately of what appears to be a backfilled trench, 5 meters by 2 meters by, meter 7 deep or something like that. Now, this is a trench that is said to contain the remains of approximately 70 men. And that might seem like a rather small trench for that purpose. But in my conversations with people who work in this field, in forensics and criminal justice, to a person, they tell me, it's a bit of a grim observation, but you would be amazed how many bodies can be placed in a relatively small trench. So for now, this is looking like a legitimate target, and it's something that we need to ground truth with follow-up excavations. So that's just something we've not yet planned and scheduled, but it's coming. And the final case study is the SS Atlantic, which was a shipwreck, a Victorian shipwreck, early April. I think it was April 1st, in fact, 1873, if I've got my years right. And it was one of the deadliest shipwrecks prior to the loss of the Titanic. Many hundreds of people lost their lives as a result of this wreck off the coast of Nova Scotia down by Terence Bay, when the ship actually ran aground in the dead of night. The whole stern section of the ship immediately flooded, and people were trapped inside. And it was, of course, the conditions were as brutal as you can imagine. Dismal situation. There were a couple of mass graves established nearby in Terence Bay. And this is the only photograph we have of one of the mass graves, in which the community is here seen burying the victims. And if you look closely, this is in the Nova Scotia archives, of course. If you look closely, you can see the ends of coffins already underneath the ground where these people are standing. We'll see other coffins forward and apparently additional coffins underneath. So there are multiple layers and rows of coffins here. This looks like a sledge or something, probably being used to drag coffins to the site. Now, this burial site remains known and is memorialized, but the precise boundaries of the mass grave were kind of lost, a little bit uncertain in popular memory. And about 20 years ago, a little over 20 years ago, coastal erosion here started to expose bones, and it alerted community members to take action and see what they could do to shore this area up, kind of fortify it with armor stone, but also interpret the site better and try to protect it. So a couple of years ago, just the season before COVID, I went out there with my students. Community members asked us to come out and see if we could help to define the boundaries of the mass grave. And so just give you a quick video showing the radar being used in that context. Nice wind, very authentic coastal Nova Scotia wind, and salt spray. We were all covered in it. Here we go, coming up to the end of the survey line. Now, the salt spray is relevant in this case, as we'll see in a minute. This is an aerial view of the site, a little bit of a pixelated photograph. Apologies for the quality, but these are the two grids that we surveyed. This is metal interpretive sign. So whenever we're doing geophysics and we're working in places with lots of metal signs and things, we don't get too happy about that, but it makes quite a mess of the data. This is the monument, and there's sort of like a cairn commemorating the site, the wreck, and a series of tables where people can sit, look out at the water. But this is a conductivity map using the EM38 instrument, the orange one that I showed you a moment ago. And what it does is it measures how easily an electrical current can pass through the soil. The background values in this case are this purple. And as we move up through blue to teal to green, yellow, orange, red, we're getting more conductive. So this is something worth bearing in mind because there's a very definite pattern here. And yet there's also it grades within the pattern. It gets quite conductive. Very interesting. Now, this is a radargram of that site. And on the left, this is starting down by the water. And on the right, this is upslope. Now, the first thing I'm going to point out is that everything on the left is attenuated. You'll notice there's very little actual data over here. Lots of reflections over here. In fact, this is mostly rock, bedrock. But over here, virtually nothing. And the reason for that, we anticipate, is because this area closer to the water is just impregnated with salt from salt spray coming up from the waves striking the shore. And that is a source of soil conductivity, and it interferes with the penetration of the radio wave. So when the wave wants to move down through the soil, what it's actually doing is hitting this conductive salt and then spreading laterally. And therefore, we're not really seeing much closer to the shore. That's annoying. But this is the other thing I wanted to show you here, is that you can actually correct the topography if you have the right instrumentation. So coming back to our radar for a second, you'll see, and here's Adina Fox pushing the radar up the hill. You'll see there's a device on the top of the radar. It looks kind of like a pie plate. It's on a little stick. And that's a very high precision GPS. So because we have that, we are able to correct for that slope. And I mention this because if you ever find yourself in a program where you're looking for burials and you're on a slope, make sure you have a technician or the people who are doing the survey, make sure they've got that slope correction, because once you do that, you'll see that certain patterns of reflectors can appear to be bedded more horizontally than they might appear to be if you don't have the ability to correct for slope. So that the planar reflectors are down at an angle, very difficult to determine what's going on. So in the case of this site, there's a whole area where we could not discern the burials on account of the salts in the soil. But nevertheless, we did find a series of these green lines indicate what we think we have are burials here. So it's actually quite an extensive area. The yellow dotted line indicates the area currently roped off and interpreted as site of the mass grave. But our data suggests that the area is actually much, much more extensive. And this is, of course, only one of more than one mass graves in the area. Again, the attenuation in this case caused, we think, by coastal salts. Nevertheless, slightly more conductive, this whole area, which might also be a reflection of the mass grave trench itself, holding moisture better than the surrounding soil. So it's always a good idea to have, let's say, multiple methods. Okay, so I've actually reached the end of my prepared comments, 3 case studies, but I thought I'd end on this shot. This shows us the site of Grand-Pré National Historic Site. Once again, looking north over the marsh, the old willow trees, decrepit willow trees, which almost 2 centuries ago were described as the old failing French willows. Well, they're still there, still growing. And you can see the tire tracks in the grass caused by our parallel survey transects. I'll end, I suppose, where I began, by suggesting that geophysics and archaeology, I guess more broadly, allows us a way of connecting the scholarship and the science and the study of genealogy to place, and that once that connection is made, I think it allows for a deeper and more intimate connection with those who came before us and their stories. At least it's always seemed that way to me. Okay, thanks for your attention, and questions most welcome.
Excellent. Thank you so much, Dr. Fowler. That was fascinating. I hadn't realized that there were that many mass graves in Nova Scotia. But when you start talking about, historical battles and disasters, and I started thinking, well, okay, yeah, I guess there would be quite a number of them. Um, how often are you asked to help on these types of projects, and are they government funded or are they privately funded?
You never know what's in the email, so every now and again, I'll be asked about something like this. Sometimes it's private researchers looking for an ancestor. Sometimes it's a person looking. I've had cases where people are asking to help find a family member. Often, these are cases where perhaps there's been some foul play or some, sort of like a clandestine burial. There's a case I'm looking at right now in Cape Breton that involves uh, reported uh, murder from, well, almost a century ago. Um, I had a case a couple of years ago in which a gentleman asked if we could help find the remains of his grandfather who took his own life. He suffered horribly from physical and mental health issues arising, I think, from the physical health issues he had, and he took his own life. But consequently, the community wouldn't let him be buried in the cemetery, and he was buried over in the Verge somewhere. So his family wanted to try to, find his grave. So sometimes things like that come up, and sometimes there's zero funding. In fact, often there's zero funding or very limited funding, and consequently, we can't do everything. But we do what we can, and sometimes I'll loop it into a research project with my students. So if it's close by, if we can get there, we may try it out. Sometimes larger projects, farther afield, they require more complex funding and that. So it's a real mixed bag, actually. I'm interested in doing the work for all those reasons, all those good reasons, but also for the science to try to just learn more about how the instrument functions and develop our skills a little bit.
Mhm. And do you think we've kind of hit the limit of the type of resolution and information that we can get, or are the instruments always improving, or are they getting better, or are the costs coming down? Is that kind of trend happening?
It is happening. The instruments are getting better without question. What's particularly getting better is the software. And this type of software that we use, that I've been using for almost 20 years now, called Surfer. And it's a 3D visualization mapping gridding software developed in Colorado, actually. Um, but they've just added a 3D visualization functionality, which didn't exist up until a few months ago, 6 months ago, or something like that. So every new iteration in the software allows us to do something a little bit more powerful in terms of analysis, which is very exciting. It's nice to see the thing advancing, and then we're able sometimes to revisit old data sets by plugging them into new softwares, trying new analytical procedures. So yeah, it's an exciting time to be doing this. I started in archaeology in the 1990s as an undergraduate, and yeah, that was great too. But we didn't have this kind of ramping up of innovation. So it's a very exciting time for my students, I think, right now to be just coming up in the discipline.
That's yeah, very exciting about what could be happening in the future here too. I have a question here from Leo J. DeVoe, actually, and he's asking if the graves identified on the Grand-Pré site, um, those clusters that you were seeing in the 289 identified, do you think those could possibly indicate family groupings?
Yeah, it's possible. It's possible. We're reaching here one of the limits of the technology, in the sense that I've sometimes asked, can we identify the person in there? And actually, we can't. What the radar is doing is it's detecting basically the grave shaft. It's detecting sometimes the edges of the cut, typically the bottom of the grave shaft, where you get this great planar reflection from the bottom of the cut of the grave. It's not a bone detector per se. It doesn't see skeletized human remains, and there's no way to directly assess the identity of the individual in the grave. All we have is this proxy of spatial patterns. Now we can draw inferences from those. So sometimes when you see clusters together, you might wonder, okay, did they die all at once, or is it the same family group? Things like this. But the only other thing one could do would be to actually conduct ground truthing excavations, get in there and see if there is any uh, skeletal tissue or hair or teeth or anything like that remaining, which would allow for potentially some kind of DNA analysis or other forms of analysis. But we never really get into that. And there's a whole series of the ethics surrounding that has gotten much more complex, and the policies and procedures around that are much more complex these days as well, at least in this jurisdiction. So hard to say for sure, but all we can do is produce the best mapping and then put it out there for community members and others to speculate and draw inferences. And my guess would be that some of these behaviors and patterns would persist, so that later Acadian cemeteries might be organized in similar ways, for example, particularly of those kin groups, so the sort of families that buried in Grand-Pré prior to 1755. If we can track them and see their behavior in the next generation and the next generation in cemeteries that are better marked, perhaps we might be able to draw inferences about what we're seeing in Grand-Pré. I hope that answers the question. It's a bit of a roundabout answer.
No, that's great. We're running short on time, so probably only one or two questions more. Someone's asked if there are other sites that you have on deck to be studied in the future.
Yeah, a very exciting one. In fact, I'm glad that question came up because I would have forgotten. I was going to try to shoehorn in some comments about Windsor Falmouth. So starting on Thursday this week, which is April 27th, I'm starting a remote sensing field school with my students at St. Mary's, and we are going to be in Windsor, um, possibly by that end of the week, or certainly the week after, Windsor Falmouth, and we are going to be mapping with the same techniques, starting with the Sainte Famille Cemetery in Falmouth. So some of you may be aware of that cemetery. It was accidentally discovered by a construction project in 1996. And it's an unmarked Acadian pre-deportation cemetery, 1698 to 1755 is going from memory. And we know basically where the cemetery is, but nobody's ever mapped the individual graves, or we've not quite determined the boundaries. So we're going to try that out. And you're welcome to join us and pop by for a visit and see the work and maybe push the radar a little bit if you like. In addition to that, we'll be across the river at Fort Edward National Historic Site, where we're looking for the old Garrison Cemetery, which dates from 1750 when the fort was built, Fort Edward, and it was used by the soldiers and by the town up until 1780s, early 1790s at least, when the town built a church elsewhere and moved their cemetery to that location, and this site was abandoned. Now, this second site, this Garrison Cemetery at Fort Edward, really intrigues me because we know there was an Acadian parish church on top of Fort Edward up until 1750, and its cemetery is not exactly well known. Its location is not well known. So my suspicion is that the Garrison Cemetery at Fort Edward might be reoccupying the Acadian Cemetery for that parish church. So this will almost certainly turn into a multi-year investigation, but we'll take our first shot at those in the next 2 weeks, and everybody's welcome to come by and take a look. I'll be posting little updates on my research page on Facebook as well, which is called Archaeology in Acadie, if you want to take a peek.
That's terrific. Yeah, we'll post a link here in the chat so people can go check it out. Thank you so much, Dr. Fowler. Really appreciate this. Wish we could have you on much longer, but maybe we'll check in with you in a few years and see if you could give another talk again so we can find out about the outcomes of your research.
Anytime. You'd be most welcome to give me a ring. Thanks for this.
Terrific. Thanks so much.
Okay. Take care.
Bye bye.